Okay, so good evening to all of you. Today we are going to discuss about the week 7 lecture of Introductory Organic Chemistry Part 1, which is an platform course. So, just wait a second. So, good evening to all of you. Today we are going to discuss about the week 7 lecture of Introductory Organic Chemistry Part 1, which is the NPTEL platform course, and the course instructors are Professor Harinath Chakrapani and Professor Neeraja Dashaputre from ISER Pune. And I am Simran, your PMRF teaching assistant. So I have discussed about the till six lectures are discussed till now, and all of the lectures I have uploaded on the YouTube channel. So I hope it is clear to all of you till now what I have taught you. And if you guys have any doubt regarding the previous videos, please ask me here so that we can start up with our new session of week 7. So if you guys have any doubt, any queries regarding the previous lecture, please ask me right now. Any doubts you guys have, please ask. Okay, if there is no doubt, then I'm moving forward to week 7 lecture. So, guys, it is about substitution and elimination reactions. So, what we have studied till now is the addition reactions of alkynes, and today we are going to discuss about the substitution and elimination reactions. So, substitution and elimination reactions are the reactions which is operative in the basic medium generally, or we can say that it can be after the substitution and elimination. Substitution will replace your one nucleophile with another, but elimination will give you the generation of alkene alkynes. So here we will be discussing about some of the these kind of reactions. So I'm starting with problem number 1. So here in the problem number 1, the question is the major product P of the given reaction is. So you have to identify the product P which will be generated after the reaction of this sodium ethoxide in ethanol with this particular moiety. So here you first of all have to understand what kind of reaction is operative here. Is it a substitution reaction or a elimination reaction? So, as you can see here, the base is employed. That is a very strong base. That is sodium ethoxide. It is a very strong base, and in part of this, you have also the ethanol added. So, the base in this medium will abstract a proton. See, whenever you have seen a very strong base used in a reaction, you will immediately come to know that it will abstract a proton. So basically, here also the sodium ethoxide, being a very strong base, will abstract a proton from the substrate. So from the reactant, the abstraction of the hydrogen will take place now. So now where will be the abstraction of hydrogen takes place? Now you have to look at that aspect. So now there are two chiral centers are present here. See. So either this hydrogen will get abstracted or this hydrogen ion will get abstracted because there are two possibilities only. So here in the case of chiral center 1 and chiral center 2, if you abstract a hydrogen from the carbon number 2, then you will end up having a negative charge on this carbon. But what will happen next? What is the fate of this carbon ion that is generated in the at the center? Now the fate of this carbon ion is it will do elimination. But as you can see, this bromine is attached to the same carbon on which you are going to generate a carbon ion now. So the leaving group and the carbon ion both are present on the same carbon. So that is why there is no fate for this particular carbon ion to give you any elimination reaction. Or substitution is not possible in this case because of the presence of very strong base. You will end up having a hydrogen abstraction. So now it is clear that carbon number 2 is not going to give you the proton you needed, right? Because there is no elimination further which will be possible the if you abstract the proton from this carbon number 2. So here the base will then abstract this proton that is present on the carbon number 1 to give you what? A carbon ion is getting generated here. A carbon ion is getting generated here, and this carbon ion then this will get delocalized and this Br will knock out. So this is a standard example of a E2 elimination, that is the E2 elimination. So elimination reactions are generally of various types, in which you will see that this is the E2 elimination that is operative here. So here hydrogen is taken out by the base, and you will end up having a alkene in the system. How? See, this proton is taken by base, and this is how the alkene generation will take place. It is the E2 elimination that is operative in this particular reaction. E2 means the trans elimination. Here the hydrogen which is getting eliminated and the Br, that is the leaving group, should be anti-periplanar to each other. Anti-periplanar means it should be anti in configuration with this hydrogen and Br to get leaved out. E2 elimination has a rule that both the proton and the leaving group should be anti-periplanar to each other so that it will get generated a alkene. So this is the basic concept behind the E2 elimination. So now, if you understand that yes, E2 elimination is taking place here, as you can see now you have to assign the positions of this substituent that is present at the chiral center. It is clear that alkene is getting generated. But now, what kind of alkene is this? Is this fourth, second is not a alkene, first. Now the second and third will not going to give you this product. That is why you can simply eliminate those options. So second one is also not the product and third one is also not, because in the third option there is substitution that is taking place, but in the presence of very strong base you cannot see that substitution is taking place. Always elimination happens first. So here you have to now figure it out that which will be the answer, first or fourth one. What could be the possible answer? So now for this you have to assign the stereochemistry. So you need to first draw these things into Fisher projection. First of all, draw these things into the Fisher projection. I'm drawing this carbon number 1 and carbon number 2 in the Fisher projection. So I have told you guys how to draw these Fisher projections. So if someone doesn't know how to draw it, please refer to my previous videos. Then you will get to know how I'm drawing these Fisher projection. This is methyl, this is hydrogen, and again this is what methyl looks like. This will be pH, right? This will be pH. So now this is the Fisher projection. Now to understand the stereochemistry and to visualize which is the anti-periplanar bond, you need to draw the Newman projection. So here in the Newman projection, I have told you the Newman projection is the eclipsed form of Fisher projection. So now here you can draw these things. So after H, you have this methyl here and this pH. Now drawing the eclipsed configuration. So here you will have this methyl again and hydrogen this side. Right, this is how I'm going to draw this. But now you have to see the anti-periplanar bond. So that means this hydrogen and Br should be anti-periplanar to each other, which means they should be opposite to each other. So now draw the staggered conformation of this particular Newman projection what you have drawn already, and you will get the answer. See, here it is methyl, here it is phenyl, right? And this is hydrogen, this is what? This is methyl. So this is what you have now. So you can now see this hydrogen and Br, they are anti-periplanar to each other. Now, if it is getting eliminated like this, then what alkene you will have? You will have a alkene in which these two methyl groups are on same side. And this will be again pH and hydrogen. So you will end up having this alkene. So this is how the E2 elimination and the respective stereochemistry you can assign for these things. Similarly, I have showed this example. So in this also, you have to show this hydrogen and the leaving group antiperiplanar to each other, and to assign the antiperiplanar geometry, the rest of the substituent, you can assign the stereochemistry for that. So here the pH and Me are coming on one side, and hydrogen and pH is coming on one side. So that is how you can relate. First of all, draw the Fisher projection, and relative to that, draw the Newman projection, that is eclipsed. Now eclipsed should be getting rotated, and draw the staggered projection for the Newman projection. So here, after getting the staggered form of the Newman projection, you can see clearly that which substituent should be lie on one side and which substituent should be lying on another side. So this is how you can assign the stereochemistry of the substituent that are attached to the chiral center. So here, after getting this alkene in hand, you can clearly say that between 1 and 4, which will be the answer now? The option number 4 will be the correct one. So here you will have this alkene as a product P. So the value of P will be option number 4. So is it understood to all of you? Anyone has any doubt? Is it understood? Please respond. Okay, if there is no problem, then I'm moving forward to problem number 2. Okay, so problem number 2. So it is asking what is the major product for the following reaction. So now you have to identify the major product of this reaction. So again you have the sodium methoxide and methanol in the system. I have told you that sodium methoxide are a very strong base. So what they will do in the reaction, they will abstract a proton. So now you have to look at where is the leaving group present. It is also the example for E2 elimination. Why? Because here also you have one leaving group that is present, and the strong base medium is also present. So here in the strong basic medium, you will abstract a proton from the surrounding, and what you have is the alkene, and now you have to identify from where this alkene bond is getting formed, right? So here, as you can see, there is a above the plane hydrogen that is present. Here, there is two hydrogen that are present. One is above the plane and one is below the plane. So this is below the plane hydrogen. This is above the plane hydrogen. So, and in the adjacent, what you can see here is if the E2 elimination is operative, I have told you the E2 elimination has one rule, one condition, that both the hydrogen and the leaving group, the hydrogen which is getting abstracted and the leaving group should be anti-periplanar to each other. Matlab, it should be opposite to each other. Only then it will goes E2 elimination and it will give you the alkene. So here we have to look out. We have to look now which hydrogen is present anti to Br, so that they both can get eliminated and form you alkene, that is via a E2 elimination mechanism, right? So now in this case you have to look which hydrogen should be leave out. Either this hydrogen, if this will leave out, then you will have a alkene that have this double bond. If this hydrogen will leave out, then you have an alkene with double bond this side, right? So now you have to look whether the compound 1, compound 2 or compound 3 is getting formed. How compound 3 is getting formed? This is also a hydrogen that is present. So here you can get abstracted. Basically this is a methyl, so there CH2 and H. After removal of this proton, they are claiming that this exocyclic double bond can get formed, right? Here substitution is taking place, so you can clearly say that substitution is not going to happen in the very strong basic condition. So here elimination is operative first. So E3, the option number 3 is getting eliminated. So now you have to look out which will be the possible answer, either option number 1, either option number 2 or option number 4. Now, in between three options, you have to look out which is the correct one. So, now coming back to the question here, see, I have told you this is the above the plane hydrogen and this is below the plane. Here, one hydrogen is present at the adjacent and that is above the plane. So, I have also told you that the rule is both the proton and the leaving group should be anti-periplanar to each other. That is, it should be anti to each other. So, now if this hydrogen, carbon number 1 hydrogen, has to be eliminated from this side, then what will be the case? What will be the requirement? That it should be below the plane because the leaving group is present at above the plane. So if the leaving group is present at above the plane, the hydrogen should be below the plane because now this H and Br should be anti-periplanar, and being anti-periplanar, that stereochemistry should be anti. If the stereochemistry is anti, only then you can say that hydrogen is going to give you the A2 elimination. Otherwise, it will not going to give you the elimination reaction. So here if you see in the carbon number 1, the hydrogen stereochemistry is above the plane. So you can relate that yes, the above the plane chemistry, and also here also it is present at above the plane. So that means this hydrogen is not going to be eliminated because it is not anti-periplanar to each other. So now coming to the adjacent carbon, carbon number 2 here. Here you have both the possibilities. Both the hydrogens are present, either above the plane, either below the plane. So the condition was that the bromo, as it is above the plane, the hydrogen should be below the plane, right? To be anti-periplanar. So here you have both the hydrogens above the plane as well as below the plane. So here you can say that yes, we can undergo a elimination reaction using the below the plane hydrogen. So this hydrogen and this Br should are anti-periplanar to each other. So yes, what will happen now? This hydrogen is getting abstracted. This below the plane hydrogen is getting abstracted by the base, and the scenario is now here. If it is getting abstracted by the base, this hydrogen, then this will goes here, and this Br will knock out. So this is how you will end up having an alkene that is positioned at this carbon. So here you will have this hydrogen and Br anti-periplanar to each other, that is why you can say that yes, this side hydrogen will go and will give you a alkene that is matching with option number which, the option number 2. So here option number 2 will be getting formed because one cannot be formed because hydrogen is upside and Br is also upside. So it is not anti-periplanar. So that is why this first is not going to form. So it is getting eliminated. Again, this fourth is getting eliminated because here there is no hydrogen. It is a methyl group, and methyl group hydrogen will not going to give you that particular elimination process. So here it is also eliminated. So the correct option will be option number 2. So option number 2, that is this alkene, is going to form when you subject this particular reactant to sodium ethoxide and methylene condition. So is it clear to all of you why the second option is the correct one? Okay, if it is clear, then I am moving forward. So here also I have showed that how this hydrogen, basically if this hydrogen is below the plane and this deuterium is above the plane and you have that leaving group below the plane, so the condition is that the proton or deuterium should be above the plane to leave out. So that is why now this deuterium will leave out, giving you alkene rather than the hydrogen. And in this case, the second one, this hydrogen will leave out and Br will leave out to give you this alkene because now they are anti-periplanar to each other, right? So now coming to problem number 3. So you have to be very careful in E2 elimination. The rule is the both the leaving group, both the proton and the leaving group should be anti-periplanar to each other for the elimination to take place. Otherwise, it will not going to take place. So here coming to problem number 3 now. So in the problem number 3, they are asking the major product form in the following reaction sequence is. So in this reaction, what will be the major product that is getting formed? You have to figure it out. So now the reaction is, first of all, it is having two parts. So one by one, we will go through what is happening in each part, right? So here, in the first part, you have tosyl chloride and the pyridine. Pyridine is a base and tosyl chloride is a protecting group. So now you have a free OH which is present in the system. So what happens? This pyridine, as being a base, what it will do? It will abstract the acidic proton. So if it is abstracting the acidic proton, then what could be the acidic proton that is present in the reactant? Which is the acidic proton? So which is the acidic proton that is present in the system? What happened? Why you have raised a hand? Any query? Any query? Anything you have? Am I audible to all of you? Oh shit. Okay, now am I audible to all of you? I'm sorry, my mic was off. I haven't. Okay, if you haven't understood anything in the previous questions, please ask me, right? So, shall I proceed? Okay, okay. Sorry for the inconvenience, huh? Okay, now, fine. Okay, so here in the problem number 3, what they are asking, the major product form in the following reaction sequence is. So now you have to figure it out which will be the major product in this reaction. So now one by one we will go through from in the second part. So here in the first part they are treating the reactant with this tosyl chloride and the pyridine. Pyridine being a base will abstract a acidic proton in the system. So and tosyl chloride is a protecting group. So here in the reactant, can you tell me which is the acidic proton which pyridine is going to abstract? Which proton did pyridine will abstract in this reactant being a base, so it will abstract a acidic proton, right? So which will be the acidic proton that is abstracted by pyridine? Any guesses? Anyone knows? Which is the acidic proton in this case, in this reactant? The proton which is connected to oxygen, that is this alcoholic proton, is a acidic proton in this medium. So here pyridine will abstract the proton from here, forming this alkoxy anion, and this alkoxy anion will then attack on this tosyl chloride. This tosyl chloride structure is this. So this is paratoluene sulfonic chloride. So here paratoluene group is present and sulfonyl group is present. So here this oxyanion that is getting formed now attack on the sulfur of this sulfonium, and this Cl will leaves out to give you this protection OTS. So this oxygen will now get protected. So now, being OH, it is not that much leaving group because OH is not a good leaving group, right? But here, after protecting it with this tosyl chloride, now this OTS becomes a very good leaving group. So OTS, OMS, nosyl, these kind of protections are there to make this alcohol a good leaving group. So here in the first case, the purposely what the reaction is doing here, they first treat with pyridine, and pyridine will abstract a proton that is acidic from the alcohol. Now the alkoxy that is getting formed in the system will attack on the tosyl chloride. So here sulfur is getting attacked and Cl is getting knocked out. So after attachment of this oxygen and the sulfur group, this OTS now becoming the very good leaving group, which was not in the case of OH because OH is not a good leaving group. So to make it a good leaving group, we have treated it with pyridine and tosyl to make OTS instead of OH, right? So now, if having OTS in hand, now the second condition is, see, it is it clear now here? This OTS protection is going to happen in the case one. So first reaction is completed with the protection of OH to OTS. Now in the second case, what they have treated it with? This is again the sodium ethoxide and ethanol, which they have treated the tosylated starting material. So here this is again a very strong base. So what does this strong base do? It will abstract a proton. So here, as you can see now, you have successfully done the job of making OH to a very good leaving group, that is OTS. And here this hydrogen that is present will be abstracted by the base sodium ethoxide. So here also this E2 elimination is operative, but now what you have to see, that H and OTS should be anti-periplanar to each other. For E2 elimination to take place, the thumb rule is the proton that is abstracted by the base and the leaving group should be anti-periplanar to each other. Anti-periplanar means should be opposite in the stereochemistry to each other. So here, if OTS is present in the plane, now you have to bring this hydrogen as well into the plane. So this carbon center stereochemistry will remain same. The methyl is above, the proton will be below. This stereochemistry is same. Now you have to rotate this carbon center such that this hydrogen will get in the plane. So here what you will get is, see, according to the Sayhorse, you can say this, see this. In the Sayhorse, what is happening? If this is pH, in the plane, then below the plane is Me, and this is hydrogen, right? I'm seeing this according to the Sayhorse configuration. So according to Sayhorse nomenclature, so here this carbon center I have drawn only, right? Because this is remains fixed. So here you have to rotate this carbon in due to make this hydrogen in plane, because it should be anti-periplanar to eliminate. So here if I want to bring this hydrogen in the plane, so what I have to do? Rotate it by 60 degree. So if I am rotating it by 60 degree, then Me becomes above the plane, phenyl become below the plane, right? So this kind of system you will arise. Now here you can see this hydrogen and this leaving group are now anti-periplanar to each other. So now they can leave. So here this hydrogen ion is taken up by this ethoxide, the base in the system. This is taken by this. Now this will goes here and this will leave out. So this tosyl group will leave out. To give you what alkene? See, the stereochemistry is like methyl and methyl is above the plane. So this means these both are at same side. So this hydrogen and pH are of same side. So this is how you will end up having this alkene in hand. So here I'm repeating myself again in the whole sequence what is happening. Here what you have is, first of all, this alcohol being, it is not a very good, it is not a good leaving group, so it will not leave out as such, because if you treat this starting material with this base sodium methoxide ethanol, you will not going to witness a elimination reaction, because OH is not going to leave out, because it is not a good leaving group. So to make it as a good leaving group, we have first treated it with this tosyl chloride and pyridine to make OH, converting into OTS, and then the sodium ethoxide ethanol will play a role of elimination. So for elimination, I have told you the two leaving group and the hydrogen that is abstracted by this base should be anti-periplanar to each other. So now you have to make OTS and H in the plane. So to make it in the plane, you have rotated the chiral center through 60 degree and you get it in the plane. So here this ethoxide will take up this hydrogen, then this hydrogen will goes here, this carbon and that is getting generated, and this OTS will leave out. So here you will get a alkene where this methyl and methyl are on same side and hydrogen and pH are on same side. So this is how you will end up having a alkene. So the correct option in between these are, what would be the correct option? Option number 3 will be the correct one, right? So is it understood, this question? Any queries, any doubts in this question? Please respond so that I can know that you are here. Is it clear, the problem number 3? Okay. Then if it is clear, then I'm going to problem number 4. So here in the problem number 4, what they are asking, predict the product for the following elimination reaction. So here what you have to predict is the product. This product you have to predict according to the elimination reaction. They have showed you that it is a elimination reaction, so now please predict what would be the product. So here they have treated it, this particular starting material, with methoxide. So this methoxide is again a base, right? It is not just, they are not writing the counter ion. So here the sodium, potassium, anything could be the counter ion, right? So here this methoxide is present as a base, and they have told you that you have taken it in one equivalent only. So you have one equivalent of base, not excess of base. So what again the base will do? The base will abstract a proton. So they have told you that it is a elimination reaction. So now base will abstract a proton either from this side either from this side, here, and here. The acidic protons are present all these four positions, right? So here you have one equivalent of sodium methoxide. So here they are telling you what will be the P. So now one by one we will go through all the options. So now in this, as you can see in the first option and second option, you have two options, either Cl or either I, either chlorine or iodine. Among these two, one will eliminate, right? So one will eliminate. So here you have to see which is a good living group, chlorine or iodine. Which is a good living group? Can you tell me which is the good living group in between these, chlorine or iodine? Okay. So here, see, iodine is a good living group. Why? Because iodide ion is very large enough. So while carrying this negative charge with it, according to Fajan's rule, what will happen? The more, the bigger the anion, it will stabilize the negative charge more. So that is why here iodine is acting as a good living group. So here, being this thing in mind, keeping this thing in mind, what you will do now? Here you will have a base. It will abstract a proton. So now you have only one equivalent. So now you want to abstract a proton. So because this iodine is a very good leaving group than Cl, it is becoming very more facile to abstract these hydrogens rather than the hydrogen which is adjacent to Cl. Because now Cl is not a very good leaving group than iodine. So there is a competition between these two because you have used only one equivalent. If you have used excess, then both of this will get eliminated, but you have used one equivalent of this sodium methoxide. That is why I'm saying that now there is a competition that is happening between Cl and iodine. So here in between these competing reagents, what you will see, that iodide is a good leaving group than the chloride. So being a very good leaving group here, so now this base will abstract the proton from this side facile readily than the this side. So here it will abstract a proton from this side. Again, this proton will goes here. This iodine will knock out to give you a alkene at this position. Right? So either this alkene is getting formed or either this alkene will getting formed after the removal of Cl. So you have given in the option number A suggests that first of all this Cl will knock out readily then iodide. Then the option B suggests Cl remains in the system, but if you are using one equivalent, first of all, this iodide leave out. Third option is suggesting that there is a rearrangement that is taking place. And D option is also a kind of rearrangement because they are saying that here a positive charge can get formed and there could be a rearrangement that is kind of Merwin Wagner rearrangement. Okay, but here there is no carbocation that is getting generated in the system. That is why this rearrangement product is not the one you will end up with. So now you have to figure it out what would be the possible answer. So based on the things which I have told you, can you tell me which will be the correct one? Option number A or option number B? Which will be the correct one? Option B. Yes. So the option B will be the correct one. Why? Because here, that as I have told you that here, iodide is a good leaving group than Cl. That is why if you have one equivalent only in the system, it will abstract a proton from this side very readily than the Cl, and here you will end up having this alkene and this Cl remains in the system. So this is how you will have the explanation that iodine is a better leaving group than chlorine. So it will, the ethoxide first tack on this proton, take up this proton, and now the carbon ion that is getting generated at this position will goes here and iodine leaves out. So what you will having is a major product. This would be the major product, and the minor one will be here where the Cl substitution is taking place, because Cl is very less better leaving group than the iodine. So here the correct option will be option number B. But if you have this base in excess, then you will end up having both the elimination. Here you will end up having both the elimination. So here you will get this product as a major product if the base is present in the excess. Both the halide will knock out and you will get this as a major product, right? So is it understood? Any problem, any query in this question? Understood. Okay. So coming to problem number 5 then. If it is understood, then coming to problem number 5. So they are asking which of the following statement is correct regarding the following reaction. So now you have to analyze what kind of reaction is this, and then you have to figure it out what would. Sorry, yes. Actually, I don't know. I am not seeing anyone here. Just you and me are here. I don't know why people haven't joined this session, because everyone is joining till the last class, but now there is no one. I don't know why people are not joining. Okay. Huh. So maybe they have some issue or something. Yeah, yeah. See, I have to teach anyhow. So that's why I'm teaching, right? So here, okay, coming back to the question. Yes, I think so. Okay. Okay. Okay, so coming back to the question. So here they are asking which of the following statement is correct regarding the following reaction. So here you have to analyze what kind of reaction is this first. Now here you can see there is a tertiary butoxide and tertiary butanol that is being reacted with your bromoalkane. So here you can see that this tertiary butoxide is although a very strong base again. So now there is a very strong base present in the system. So we have talked about it a very often that what it will do will take up a hydrogen, and as I have told you, it can be possible to take out the hydrogen from either of the side, and also this hydrogen can also be taken out from this CH methyl na. There is one hydrogen that is also taken up by this particular thing. So what happens here, if I take out this hydrogen, then the carbon ion will shift here and bromine will knock out. So this kind of product will get formed if this methyl proton is getting eliminated by the tertiary butoxide. If it is taken up by tertiary butoxide, this hydrogen and then this carbon ion will shift here and we are knockout. Similarly, this tertiary butoxide can take up this proton and it will goes here and we are knockout to give you this alkene. Either this alkene will get formed or exocyclic double bond will get formed, right? There are two possibilities that would be getting formed, right? Is it understood why these two possibilities are there? How come these two possibilities are there? Yeah. So if there are two possibilities which can be undergo in this scenario, now coming to the options, what question is asking is the option number one is major product is endocyclic alkene formed according to Sedzef rule. So I've told you about the Sedzef rule, right? Previous classes. What is Sedzef rule? It suggests that the alkene formation will takes place from that side where the substitution is high. There is fewer number of hydrogen atom that is present. So the more substituted alkene favored in this case of Sedzef rule. Sedzef rule says that the more substituted alkene formation is favored. So, first option is suggesting the major product is endocyclic alkene. What is meant by that? See, I am drawing it here. There are two possibilities. Either this endocyclic double bond, exocyclic double bond is getting formed, or this endocyclic double bond is getting formed. Ron, I'm not writing the substituent. I'm just writing the core. So this is the exocyclic double bond. This is the endocyclic double bond. They are saying that the major product is endocyclic alkene formed according to the Sedzef rule. So this endocyclic alkene, as it is more substituted, it is forming according to Sedzef rule. Fair enough. Now you have to see whether the option is right or not. Just forget about the major and minor product, and we will talk about it later. Just focus on the Sedzef and Hoffman rule, because I have told you about the Sedzef rule, but I haven't told about the Hoffman rule. So Sedzef rule says that the more substituted alkene is favored. So now option A is suggesting that endocyclic alkene, that is this endocyclic alkene, is forming according to Sedzef rule. Is it right? Yes, it is right, because according to Sedzef rule, more substituted alkene should form. So here in the option A, endocyclic alkene is forming according to Sedzef rule. Yes, yes, please. Okay. Yeah, sure. See, what Sedzef rule says, if elimination is taking place, right, then you have possibilities of forming alkenes like this. If you have a methyl group here, let's say there is a methyl group, here also there is a methyl group, right? And these are protons, let's say. So this is the substituted alkene. So now Sedzef rule says that alkene formation is feasible which is more substituted. So that is favorable. So here we have two possibilities in the case of this starting material. In the case of the starting material, what will be the possibilities? See, I'm erasing everything and just see. So try to focus on the starting material here, this starting material. So there are two possibilities in the starting material. Either this hydrogen will get eliminated or this hydrogen will get eliminated. So if it is getting eliminated, then what you will having a alkene that is getting formed inside the ring, right? But if you form this particular alkene, then the exocyclic alkene is getting formed. So just tell me, which is more substituted, the exocyclic alkene or the endocyclic alkene? Which is more substituted alkene? This is again Me. See, exocyclic alkene having more number of hydrogens rather the endocyclic. So if you are worrying about the endocyclic alkene here, just focus on the double bond. I'm saying this double bond, that is exocyclic, having two hydrogens, right? But here, if you focus on the endocyclic alkene, if I am focusing on the endocyclic alkene, this alkene has lesser number of hydrogen and is more substituted. See, here methyl is there, second position is methyl is there. Here also methyl is there, and again one hydrogen is present only. But here there are two hydrogens and two methyl groups that is present. So that is why we are saying that this endocyclic alkene is much more substituted than the exocyclic alkene. Is it understood why it is more substituted the endocyclic alkene? See, this endocyclic alkene, as it is more substituted and the exocyclic is less substituted, so what now Sedzef rule says that alkene formation is more favored, which is more substituted. So now the formation of this endocyclic alkene, that is this, is according to Sedzef rule, because now here more substituted alkene is getting formed rather than the less substituted alkene. So that is why the the option number A is saying the right thing. Just forget about the major minor product now. Here I'm saying that the endocyclic alkene is forming according to the Sedzef rule. Right? Is it clear now why it is forming according to Sedzef rule? Because it is more substituted than the exocyclic. Right? Understood now? Yeah. Now coming to option number B. See, option number B is saying exocyclic alkene is forming according to Sedzef rule. Is it right? No, because now here exocyclic alkene is less substituted, but Sedzev rule is saying that if you have competition between these two, formation of these two, which will be favored? The more substituted one. That is endocyclic product will be favored. This endocyclic product. So the option number B is the wrong one because it is suggesting that the exocyclic alkene is forming according to the Sedzev rule. So a Sedzev rule is promoting the endocyclic because of the more substitution. So here you can say the B option is now neglected because they are saying the incorrect statement. So now coming to option number C, the exocyclic alkene formed according to Hoffman rule. Now Hoffman rule is opposite to Sedzev rule. Sedzev rule, sorry, Sedzev rule is suggesting that the more substituted alkene is getting formed, but Hoffman rule says that if there is a competition between the formation of alkenes, that alkene formation will favor which is having least substitution. So here Hoffman rule will favor the formation of exocyclic double bond. So the exocyclic double bond is forming according to the Hoffman rule, but endocyclic is forming according to the Sedzev rule. So the both the rules are opposite to each other. Sedzev rule is saying whenever there is a competition between the formation of alkene, those alkene is favored, which is more substituted. But the Hoffman is saying that the least substituted double bond is favored. So have now you understood what is the difference between the Sedzev and Hoffman rule? Is it clear to you? Okay. So now if it is clear, then the option C is saying that the exocyclic alkene formed according to the Hoffman rule. Is it right? Yeah. So it's correct. Now D, coming to the option number D, they are saying the endocyclic alkene is forming according to the Hoffman rule. It is incorrect. So now based on the information about Setzeff and Hoffman rule, what is it? You are now neglecting two options. Right? Now you will left with A and C. Now you have to see which is the major product. Now the question comes, which will be the major product? So now the stabilization will see told you that which will be the major product. So now coming to this, here two products are possible: exo due to Hoffman, endo due to Setzeff. Now you have to tell me that which will be the major product. See, the endocyclic alkene is less favored because of the steric hindrance. Here there is a steric hindrance. Exocyclic alkene are more stable because steric hindrance is not there. These are two hydrogen that are present here, and in this case you have hydrogen and methyl, so there is a steric hindrance that is operative in this particular region. But if you compare it with the exo product, there is no steric hindrance in the alkenes. So if you compare the stability, and if you want that you want to figure it out which is major, which is minor, then you will say that always that alkene which is exocyclic is stable than the endocyclic one because of the less steric hindrance in the case of exo product. Is it clear now? Okay. If it is understood, then what will be the correct option between A and C? A is saying major product is endocyclic alkene formed according to Sedzeff, or C is saying major product is exocyclic alkene formed according to Hoffman. Which will be the major product now? Option number? Option C will be the correct one, right? Yeah. So someone wants to join, I think. Yeah. Okay. So option number C will be the correct one. So now coming to problem number 6. So in the problem number 6, what they are asking now, the select the reaction pathway and the major product form for the following reaction. So now you have to identify the reaction and you have to select the reaction pathway as well as the product which is getting formed. Here I have told you that this sodium is having a positive charge and this sulfur is having a negative charge. So now the condition is you have a leaving group in the system Br on the starting material, but you don't have any strong base in the system. This moiety is not a base, is not a strong base. It is a nucleophile. It is a nucleophile. So here, from here, you can see there is no elimination that is possible in this case because you have a leaving group, agreed, but system doesn't allow you to give the elimination because there is no strong base that is present in the system. There is a nucleophile that is present in the system now. So the reaction pathway is not a elimination pathway, rather it should be a substitution pathway. Now, if it is substitution, then E2 and E1 elimination reactions option is getting eliminated. Why? See, you have to see very carefully when substitution and when elimination is happening in the system. Elimination is supportive where there is a very strong basic medium and you have a proton that can be abstracted and a E2 kind of elimination or even kind of elimination could take place. But here in the system, you can see there is a living group that is present on the reactant, but strong basic medium is not present. So there is no base that is able to deprotonate the hydrogen and although then give you a alkene. So here the option number 3 and 4 is getting eliminated because there is no elimination reaction that could be possible in this case. There is only substitution reaction that can be happen. Is this up to here clear to you why elimination cannot be happen in this case? Okay. See, for elimination to happen, I have told you previously, in the previous case, see, compare it with the previous situations. In the previous situation, what you had is a strong basic medium. In all the cases, you have the strong basic medium, right? In all the cases, you have that strong basic medium, right? But in this case, the sodium, the methyl sulfide, it is not a base, right? It is not a base. Even though the strong base, it is not even the base. So it is not going to abstract any proton from the system. So here, if the abstraction is cannot be takes place, then there is no carbon ion that can be formed, and the carbon ion that can goes here and leave out the Br, right? So that is why there is no elimination reaction that can happen here. Instead, the sulfur negative is a nucleophile. Rather than the base, it is a nucleophile. So now you have to be very careful in the system what they have given you. Is it a strong base? Is it a strong nucleophile? You have to differentiate between these two things. Right, tertiary butoxide, sodium methoxide, sodium ethoxide, there it is very strong base. But here when you are saying about the sulfur moiety, it is not a base. It is a nucleophile. So that is why if there is no basic medium, strong basic medium present in the system, then there is no deprotonation. Abstraction of proton can take place, and if there is no abstraction of proton, carbon ion is not going to form. If carbon ion is not going to form, then elimination and the leaving group removal is not going to take place. So that is why elimination is not operative here, and only what you left with is the substitution because you have a nucleophile in the system. Now it is clear now is okay, got it. So then we will think about now which of the substitution reaction is now operative here, right? So this E2 and E1 elimination options are getting cancelled because elimination is not possible. So now you are left with only two options, that is 1 and 2. You have to figure it out, is it a SN1 or is it a SN2 reaction? So I am telling you about the basics of SN1 and SN2. SN1 reaction is the nucleophilic unimolecular nucleophilic reaction. Just a second. Okay. Fine. Okay, coming back to the question now, here you have to see whether it is SN1 or SN2 reaction. So the coming to the basics of that, SN1 is the substitution unimolecular nucleophilic reaction. Here SN2 is substitution bimolecular nucleophilic reaction. So here in the SN1 reaction, what you have is, first of all, leaving group will leave out and you will generate a carbocation here, and that carbocation is then trapped by the nucleophile that is present in the system. It is the SN1 reaction. So in the SN1 reaction, first step is the removal of the leaving group and the formation of carbocation. Second step is the nucleophilic attack on that carbocation, right? But if you go to the SN2 mechanism is a concerted mechanism. So here, removal of the leaving group and the attack of the nucleophile is a concerted process. So there is a transition state that is going to generate, and it will SN2 will give you the inversion of the product, but SN1 will give you the racemic mixture of the product, right? So this is what the basics of SN1 and SN2. I hope you guys already know it, but I'm just brushing up the concept for SN1 and SN2. So is it clear the difference between SN1 reactions and SN2 reactions? Or I have to repeat? What happened? Okay. Okay. It's okay then. Okay, fine. I hope you have heard me now. So here, what we are talking about is SN1 and SN2. So here, as you can see, if the bromine will leave out, there is a carbocation that is now going to form at this position. So this will be the carbocation that is secondary, and it is a very strong nucleophile, so here it will attack on this carbocation if SN1 is operative here. But if SN2 is operative here, then clearly there is no carbocation generation takes place, and this sulfur will again attack on the carbon here. Concertedly Br will knock out. So this is how the reaction mechanism will go. First of all, this sulfur, as being a very strong nucleophile, and DMF being a no, being a polar aprotic solvent, so here it will, what happens, SN2 is operative here. Sulfur first of all attack on the carbon, this Br will knock out, and you will generate a transition state that is pentavalent transition state, which is there in the case of SN2. So here a pentavalent transition state will take place, and inversion in the configuration will observe. So here if the Br is leaving out from above the plane, then the product will be having a below the plane stereochemistry. So there is an inversion in the stereocenter. So this is how the SN2 pathway is operative here, because SN1 is not operative, because the secondary carbocation is not stabilized here, because here there is nothing to stabilize this carbocation, right? So the stability of this carbocation is very less because there is no substituent that is present to stabilize this carbocation. So that is why, and also in the polar aprotic solvent, what you have, SN2 is favored. So in the polar aprotic solvent, SN2 is favored, and also the sulfur is a very good nucleophile, and also this carbocation is not getting any other stabilization from the substituent. What mechanism is operative here? Rather than the SN1, you will have the SN2 which is operative in this case. So this is how the reaction pathway goes. So the reaction pathway is SN2 rather than SN1, it is SN2. And what you have is inverted product. What you mean by inverted product? You are starting with R and you are having the product S. That means there is an inversion in configuration that is happening. So if Br is leaving out from above the plane, the nucleophile that is getting attacked on this carbon has no choice other than to attack from below the plane. So from the opposite phase, the attack of nucleophile takes place and the leaving group leaves out to give you this product. Is it understood, the mechanism? Okay, if it is understood, then the correct, sorry, why it is coming from opposite side? Okay, see, just imagine if your leaving group is above the plane, right? So there can be two faces at the carbon. One is above the plane, one is below the plane. Already your Br is above the plane, so it is blocking one side, right? And your nucleophile has to come, so it will prefer that end which is less substituted, right? So if you compare this, Br is above the plane and what you have with this side, hydrogen, which is present at below the plane. So now your nucleophile will attack from below the plane because one side is now blocked by Br. So due to sterics, nucleophile wants to have a phase where which is less sterically crowded. So it is coming from below the side from the second phase, because first phase is blocked. Above the phase is blocked from this side. And if nucleophile has to attack, it should have to come from the opposite side of the leaving group. So if the CBr bond is getting cleaved, then the CCS bond is getting formed from opposite side. So one side is blocked, and the nucleophile, because of the steric hindrance, wants to come from a less hindered side, which is the below the plane, as hydrogen is present below the plane, right? So that is why it will want to come from the below the side rather than the above the side. Is it clear now? Okay. So that is why now here the inversion of configuration will takes place. Now if you are starting with above the plane Br, you will end up having below the plane nucleophile. So what will be the correct option now? We have eliminated third and fourth previously. Now what will be the correct option between 1 and 2? Which is the reaction pathway and what will be the major product? Yeah. So the second option will be the correct one, because the operative reaction pathway is SN2 and the major product will be the inverted product. So here you will get this product, right? So I hope it is clear to all of you. And I'm moving forward to problem number 7. See, it is a very easy problem number 7. So I, sorry, yeah, yeah. SN1 product. Yeah, these are the products. See, in SN1, what is happening? A carbocation is getting generated, right? So this carbocation nucleophile, if I'm saying that this sulfur is a nucleophile, right? So now nucleophile has liberty to attack either above the plane, either below the plane, right? It has opportunity to attack either sides because there is no steric hindrance kind of thing now, because there is a carbocation, right? So there is no leaving group hindrance or something like that which is operative here. So nucleophile has options to attack either above the plane, either below the plane. So if it is attacking above the plane, you will have this, sorry, below the plane it is, you will have this. If it is attacking above the plane, you will have this. So in the reaction, you will have a racemic mixture because both the enantiomer is getting formed. So the racemization is going to happen is SN1, whereas in SN2 stereochemistry is fixed. So the nucleophile has to attack from the opposite side of the leaving group. So there is only one configuration, one product that is getting formed. Right? Is it clear? Okay. Now coming to problem number 7. Problem number 7 is a very easy question, guys. So I think without any further explanation, you can answer this. So the question is the order of leaving group ability of the following is. Now you have to arrange according to the order of leaving group ability. Fluorine, chlorine, bromine, iodine. Which will be the most able leaving group and which is the least able leaving group. So now can anyone answer me what could be the right answer? So the leaving group ability you have to justify whether the iodine, bromine, chlorine, and fluorine, which is the most readily able leaving group and which is the least readily able leaving group. Yeah. So what would be the correct option? Option B. Yes, option B will be the correct one. Now, for those who doesn't understand what is the concept behind it, see here what is happening. You have to assign the leaving group orders. So, with the leaving group, what it means that fluorine is now getting a negative charge. Fluorine is getting a negative charge. So as the chlorine is getting a leaving charge, negative. Here also negative charge is getting generated after removal. I'm talking about here also iodine negative charge. So now which is the species which is now very much stabilizing that negative charge? If the negative charge is getting stabilized on one species, that means it is most readily available for leaving. So here, according to Fajan's rule, you can go through these postulates that size of ion and charge of cation matters. So here, greater is the greater is the size, larger is the size of the anion, greater the covalent character of the ionic bond, which means greater is the stabilization of that negative charge. So here, if the atomic radius is going to increase from this side, as fluorine is smaller than chlorine, chlorine is smaller than bromine, and bromine in turn is smaller than iodine. So iodine being the largest anion in the atomic radius I'm talking about, if it is having the largest atomic radius, then according to Fajan's rule, what happens? The negative charge is very much stabilized on iodine because of the atomic radius. So bigger is the anion, better is the stabilization of the negative charge. And smaller is the cation, better is the stabilization of the positive charge. So this is how you can say that smaller is the anion and larger is the size of anion, the stabilization of charges are there. So according to this rule, you can go through that if the atomic radius is increasing, if you are going from chlorine, bromine, and iodine, that means the negative charge stabilization is getting increased in that way. So if iodine having the maximum stabilization of the negative charge, that means it will prefer to leave out very readily. Then bromine, which in turn prefer leaving out readily than chlorine, which in turn will prefer leaving out than fluorine, right? So here fluorine being the very smallest anion, it is stabilizing the negative charge very least. That is why it will prefer leaving out least, right? It doesn't it doesn't follow the order of leaving out very fast. Fine. So here iodine being the larger one stabilize the negative charge highly, and that is why it is the best leaving group. Then Br, then Cl, and then fluorine is the least uh, least readily available leaving group, right? So I hope it is understood to all of you why the leaving group order is that iodine, bromine, chlorine, fluorine. Any problem, any query in this question? If not, then I'm moving forward. So coming to problem number 8. So here, can you please mute your mic? Yeah, thank you. So here in the problem number 8, What you have to answer is choose the correct statement. So now you have to comment which is the correct statement. DMSO is a polar protic solvent while DCM is a polar aprotic solvent. Now you have to answer about the polar protic and polar aprotic solvents. First of all, to understand what is the polar protic and what is the polar aprotic solvent, this is the definition. So here, polar protic solvents contain hydrogen. Can you please switch off your mic? Yeah, thank you. So here, polar protic solvents are the solvents that contains a hydrogen atom bound to an oxygen or a nitrogen, right? That contain a dissociable proton. So here, these are the some polar protic solvent. So here, acetic acid, when you dissolve it, it would give you a ionizable proton, that is H plus in the medium. Methanol will give you methoxide and a H plus. Butanol will again give you the same thing. And this water, as you know, will give you OH minus and proton. So the solvents that will give you on dissociation a ionizable proton, that is known as polar protic solvents. But now what you mean by polar aprotic solvents? That does not contain a hydrogen atom directly bounded to oxygen or nitrogen, so it doesn't contain a dissociable proton. For example, DCM. See, this is the structure for DCM. So this is the dichloromethane. So here it has hydrogens, but it is not dissociable hydrogens. So on dissociation, it is not going to give you the proton in the system. Why? Because it is not ionizable, right? It is not acidic proton. So in the acetic acid, what you have is this acetate ion, negative charge, and the H plus, right? So that is a polar protic solvent. But here these are the polar solvents but not protic, because they are not going to give you a proton on dissociations. So polar aprotic solvents are the solvent that are polar but lack an acidic proton. So they lacks an acidic proton. So they doesn't have a hydrogen atom that is directly attached to a electronegative atom, that is oxygen and nitrogen, which is possible in the case of polar protic solvents. So here in the polar protic solvents, the hydrogens are attached to a electronegative atom and is very easily dissociable when they are going to dissociate in the system. But in the polar aprotic solvent, it doesn't contain a hydrogen atom that is directly attached to an electronegative atom and does not give a dissociable proton on dissociation. So is it clear the definition? What is the difference between the polar protic and what is the difference between polar aprotic solvents? Is it clear the definition of these two? Any doubts? Is it understood? The definitions, the meaning? Okay. If it is understood, then coming back to the problem. So here they are telling you that choose the correct one. So anyone has, actually someone just raised the hand, I think. Fine. Okay. Okay, so one by one, just come to the options. So they are saying that dimethyl sulfoxide is a polar protic solvent while DCM is a polar aprotic solvent. So this is the structure for both. This is DMSO and this is DCM. Dimethyl sulfoxide and dichloromethane. They are saying that this DMSO is a polar protic solvent while DCM is a polar aprotic solvent. So, can you tell me this DMSO, is it a polar protic solvent or a polar aprotic solvent? Yeah, because there is no proton that is connected directly to an electronegative atom and which on dissociation will give you a dissociable proton. It is not there, right? And when you are talking about the DCM, What is it? Polar protic or aprotic? Aprotic again, because there is no proton that is directly attached to the electronegative atom, and which on dissociation will give you the proton. So here, if you are understood that what is polar protic and aprotic, then just tell me which will be the correct one. Option number third option. Option number three is DMSO and DECM are both are polar aprotic solvents. So option number three will be the correct one, right? Understood? Okay. Now coming to problem number 9. So we quickly finish the problems now. So here they are telling you the order of nucleophilicity for the following anions is. This is the acetate, methoxide, phenoxide, and nitro. Which will be the highest order of nucleophilicity? You have to arrange these compounds to the nucleophilicity order. Nucleophilicity means how, which is the most strong nucleophile among these four, and which is the most least strong nucleophile among these four. You have to assign, right? So can anyone tell me what would be the correct answer? Any guesses? Nucleophilicity means which is a better nucleophile. Okay, so I am going to give you some hints and then you will tell me. Sorry. Option 1. Okay. So now what I am going to tell you, just I'm giving you some hint and then you will tell me which will be the correct one, right? You are saying one, but after listening my hint, that your answer changes or not, just have a look on that. So here these are the things which you need to know now. So here nucleophilicity. Nucleophilicity. What you mean by that? Which is a better nucleophile on which the charge is not going to spread in any other system. We have talked about the basicity, right? So what is a good base? Which is having a lone pair of electron on a negative charge, doesn't delocalize on any other system, right? So same concept lies for nucleophilicity. Nucleophile means you have very high electron density that would be present on the nucleophile to donate. Higher the electron density, higher is the nucleophilicity of that particular nucleophile, right? So here, when you come to this ethoxide, this negative charge on oxygen is not at all delocalized with this methyl, right? It is not going to delocalize, so it is remains confined on the oxygen. But when you are going through this phenoxide ion, this negative charge is getting delocalized in the system. So here it is not confined on the oxygen atom. Here also, similarly, resonating structures are there, right? Here also, it can resonate, right? Either sides. So because of the presence of resonating forms, what will happen? This nucleophilicity on the oxygen, the electron density on the oxygen is getting diminished, because now electron density is involved in the delocalization as well, right? So the availability of that anion or that particular oxygen is now reduced. So that is why you can say that the nitro having the least electron density, because now this oxygen anion is getting delocalized on both the oxygen atom. So there are delocalization on this NO as well as this NO bond. So because of the delocalization, now oxygen negative charge is not getting confined at this place. It is it is engaged or involved in the resonance as well. So that is why you can say that the electron density which is present on the oxygen ion is least in the case of nitro, right? Is it understood why nitro has the least electron density? Yeah. See, for the nucleophile to be highly nucleophilic, what is the requirement? It should have the electron density, highest electron density. So here If the nucleophile has the highest electron density, only then it would be able to impart that electron density to the next system, that to attract the electrophile, right? So here what happens in the case of nitro, this oxyanion is this anion is getting delocalized over this two C double bond O bonds. So if there is a resonance, what will be happening now? N double bond is getting formed here, and again this O minus is getting formed at this position, and as well as this position. There are three resonating form that can be possible for this nitro, na? So that is why, due to the presence of three resonating structures, this oxyanion electron density is now engaged in the resonance as well. So it is not completely confined to the oxyanion, right? It is not completely available for the electrophile donation. Similar to the concept of basicity, we say that the anilines have the less basicity than the alkylamines, because the nitrogen lone pair is now involved in the aniline delocalization, but in the alkylamine there is no delocalization. That is why we can say that is alkylamines are the basic than alanines. So similar concept arise here. So nucleophilicity, for the nucleophilicity, the electron density at the nucleophile should be highest, right? But here this is involved in the resonance. Three resonating forms are possible, due to which the oxyanion electron density is getting diminished. Is it clear now? Okay. So if it is clear, then we can clearly say that the nitro being the least nucleophilic in nature. Agreed with my statement? Okay. Coming to this acetate and then phenoxide. Can you tell me which will be more nucleophilic now, phenoxide or the acetate? Phenoxide. Why? Because there is more resonance this that is possible in this case. This oxygen is getting here, then this oxyanion is getting formed. Again, this oxyanion can go here, and this this oxyanion get formed, right? So there are more resonating forms that can be possible for this acetate, but phenoxide can has only one resonating form kind of. It will resonate with this ring, right? So here this phenoxide will behave you are more nucleophilic than the acetate. And can you tell me which will be the most nucleophilic species here among these four? Most nucleophilic. Most nucleophilic I'm talking about. See, phenoxide among these four, among these three, not among these four, most nucleophilic will be this methoxide, because this oxyanion is not at all in conjugation, in resonance, in any other thing. This oxyanion is as it is. It is not getting involved in any other thing. It is confined at this oxygen, right? So that is why you can say that this nucleophilic methoxide is a very strong nucleophile than phenoxide, acetate, or this nitrate. Is it clear why this is the most nucleophilic species, this methoxide? Anything which is not clear? Yeah, yeah. Repeat yourself what you're saying. Huh. Yeah, because see, what is the concept behind it? Your electron density is confined to oxygen only, right? Which is the nucleophilic part? Oxygen is the nucleophilic part. It is going to attack on any other electrophile, let's say, right? So what will happen now? Here your electrophile is trapping by the oxygen. So this oxy should have highest electron density, right? So in this case of methoxide, there is no resonance, there is no delocalization or any other thing which is present to spread this electron density to other thing. So this is the hole which is present at the oxyanion. That is why you are saying that yes, This is having the highest electron density at oxygen. That is why this is the highest nucleophilicity species. Is it clear now? Okay. If it is clear, then what will be the correct option now? Option C, right? Because methoxide will be the highest, and then phenoxide and acetoxy, and then this nitrate. Fine. So if it is clear, then I am going to problem number 10. So problem number 10, guys. They are saying in the reaction, if the concentration of both the reactant is double, then the rate of the reaction will be remain unchanged, quadruple, reduced to one fourth, or double. It is a very simple question. If you have seen the rate constants or something like that, Lee Chartier principle, anything. If I will increase the concentration of the reactants, what will happen? If I am increasing the reactant to double, then what will happen? The rate should be, any guesses? The rate should be, see, this is the rate law basically. So here what happens, rate of the reaction is equal to the concentration of A and B, that is the concentration of reactants. If the concentration is getting doubled, if there is twice of the concentration, then what happened, as rate is directly proportional to the concentration of the reactant, what happens, you will have, yeah, double the rate of the reaction. So if the concentration of the reactant is getting double, then the rate of the reaction will is getting doubled. So here what will be the correct option? Option number 4. Yeah. So is it understood to all of you? Any query? Okay, if it is understood, then I'm going to problem number 11. So quickly we will finish it. So here they are saying which of the following compound will not react by unimolecular nucleophilic substitution reaction. What do you mean by unimolecular nucleophilic substitution reaction? It is SN1, right? So now they are asking which of the compound will not react by SN1 mechanism. So I've told you in the SN1 mechanism, first is the carbocation generation. Sorry, option A. Don't be in a hurry. See, what I am now, just I'm giving you a guess, and then you will see. Here in the option number, in this case of SN1 reaction, first is a generation of carbocation. So let's say we are generating the carbocation. See, they are saying that it will not react by unimolecular reaction. So it will not giving you SN1 mechanism. Fine. Don't confuse it with the mechanism it will give. So now if iodine is getting leaved out, what you have, a carbocation at this carbon, again the carbocation at this carbon, and now the carbocation at this carbon. See, this is the first step in the SN1 reaction, that is the generation of carbocation after the removal of leaving group. So when the leaving group removes, I have discussed that which of the carbon will get a carbocation, positive charge. Secondary is the nucleophilic attack, right? So here, just tell me which carbocation is least stabilized. I'm saying least stable. Option, I'm saying least stabilized, guys. This is a tertiary carbocation. Is it the least stabilized carbocation? Do you think so? See, this is a second tertiary carbocation. This is a secondary carbocation. C is the again secondary carbocation, and this is also a tertiary carbocation. But guys, what you have to understand in the bridge systems, bridge system doesn't follow the same mechanisms. What happened, according to the Brett's rule, what happened, that there is there is the positive charge when it is getting generated at this bridge head. What do you mean by bridge head? This carbon and this carbon is the bridge head positions. So there is positive charge, whenever there is positive charge generation on the bridge head, it is not possible. According to Braid's rule, at the bridge head, there is no double bond that are allowed, and also there is no positive charge formation that is allowed. You can have a positive charge at this position, but there is no positive charge that is allowed in the case of bridge head when you have carbon. Nitrogen is possible, but with carbon you cannot form a bridge head carbocation and also a bridge head double bond according to the Brett's rule. So this is a very important rule in the case of bicyclic bridge systems. So you have to keep in mind whenever you have this bridge system in hand, here, if there is a possibility of elimination reaction takes place, and you will get a double bond. Say you will have a double bond at this position, double bond at this position. It is not allowed because at the bridge head, the double bond and also the positive charge, the carbocation is least stable, so it is not allowed. So that is why in this case, if there is a positive charge generation that would take place, then what will be the position? The position will be bridge head, this position, right? So because of the bridge head position positive charge, the carbocation is least stabilized. So it is not going to give you the carbocation generation. So it is never going to afford you the SN1 reaction mechanism, right? Because the carbocation which is getting generated in the system is least stabilized. That is why it doesn't want to generate a carbocation at the bridgehead position and doesn't allow the SN1 reaction to take place. Is it clear now? If you are asking, if the question is asking whether the things are going according to SN1 or SN2, you first have to figure it out what would be the intermediate in that particular situation. If the intermediate is stabilized, then the reaction will happen. But if the intermediate is not stabilized, now the reaction is not going to happen at all. Okay. So in this case, this is a standard example of what a Brett's rules say. So is it clear now? So the correct option number D, right? Yeah. Huh. Huh. Yeah. See, stability of carbocations are tertiary carbocation is more stable than secondary than primary, right? Similar in the case of SN1, the reactivity order is like that only. The stability order is the tertiary carbocation, secondary carbocation, and the primary carbocation, right? So there is no change in the case of SN1 reaction, but you have to see which carbocation is getting generated. So here, if you say among these three, this first will be the first very fast going substrate for SN1. It will give you SN1 reaction very readily because of the presence of tertiary carbocation here, right? Is it clear now? Okay, fine. And I'm going to problem number 12. So in the problem number 12, they are saying the major product formed in the following reaction is. So first, yeah, sorry. Huh. In the SN2, in the SN2, you will have primary, secondary, and tertiary. What you have said now, that is the correct sequence only, right? Okay, fine. Now coming to problem number 12. So here they are saying what is the major product formed in the following reaction. So it is the starting material. Now you are treating it with LDA. So LDA in the first or second lecture I have told you lithium diisopropylamide is a strong base. It is a non-nucleophilic strong base. So what will base do now again? Base will abstract a proton. So from where the proton is getting abstracted, can you tell me? This system has proton here and here. So which is the acidic proton? 1 or 2? Which will be the acidic proton? Can you tell me? The acidic proton will be this proton. Why? Because if you abstract this proton. If you abstract this proton, then what you will have? See, you will have a negative charge at this carbon, and this negative charge is stabilized by resonance, right? So here there is resonance, agreed? So here the negative charge is very much stabilized by the delocalization. That is why we are saying that this hydrogen is acidic enough. This hydrogen is acidic enough, it is taken up by LDA. So lithium diisopropylamide will taken up your hydrogen at this position because it is the stable carbon ion that is getting formed. So now in the second thing they have added PHCH2Br. So it is a benzyl bromide. So here benzyl bromide, this carbon ion which is getting generated here, this is a nucleophile. Now this nucleophile will attack on this CH2 and this Br knocked out. Right. So there are two possibilities I have told you, that either below the plane attack will take place, either above the plane attack will take place. So you have two possibilities. Now you have to see which is major and which is minor. Right. So is the sequence of reaction clear to all of you? We will be thinking about minor and major product lastly. First of all, this sequence will should be clear to you. First of all, LDA is a base. LDA will abstract the acidic proton. The proton which is more acidic is adjacent to the carbonyl, because now abstraction of proton will give you a carbon ion which is delocalized into the system, which is stabilized now. Now this carbon ion will attack on this electrophile and this Br knocked out. So you have two possibility, either the attack takes place from above the plane or below the plane. Is it clear to all of you? Okay. So now coming to major and minor. Now the major and minor will be dictated by the chiral center which is present in the system. Here there is a chiral center, right? So now as you can see this pH and methyl, which is more bulky, phenyl or methyl? Which is, yeah, phenyl is more bulky. So now I have told you the attack will be favorable from that side where the steric hindrance is low, where the substrate will feel the lesser steric hindrance. So, is it carbon ion? Does it feel to attack from above the plane or the below the plane? Which it will prefer, above or below? It will prefer below the plane because above the plane phenyl group is present already. It will feel very much steric hindrance if CH2PH is present at above the plane. So if the coming group is coming from above the plane, it will feel steric hindrance due to phenyl, and it doesn't want to feel that steric hindrance. So that is why it will come from that position which is less sterically crowded. Is it clear now? So here that is why this major product is below the plane, the nucleophile, and minor is above the plane because pH is already there, that is bulky. The nucleophile wants to attack the electrophile from where there is less sterically hindered site. Right? Clear or not? Okay. So I hope it is clear to all of you. If it is clear, then I'm going to the last problem of this session. This is the last problem, guys. So here you have to select the correct order of reactivity with respect to the nucleophilic substitution reaction. So what do you mean by nucleophilic substitution reaction? I'm not going to talk about this here, SN1, SN2. Here only what happens, this X is a leaving group. And here nucleophile wants to add. Nucleophile wants to add. So nucleophile can come here and this CX will leave out. So a ordinary substitution reaction is going to take place here. But now they wants to ask you the order of reactivity, which will react faster to nucleophile and which will react least to the nucleophile. It is a very important concept now, which I am going to tell you here is the neighboring group participation. Neighboring group participation. So what happens in the neighboring group participation? If this halide is getting left out, you will end up having this carbocation at this position, this carbon. Agreed? This is the carbocation position, this carbon. So here, as the neighboring group oxygen is present, this will donate the electron pair towards this carbon and will form a 1, 2, 3, and 4. A four membered ring like this. Not four, I think three. Here it is one, two, three. Yes, three membered ring like this. In the case of second, I'm talking about. And then, due to the neighboring group participation, your species, this species is now stabilized, and the nucleophile now get attacked at this position, right? And again, it will cleave out. So this is how the neighboring group participation feels like. So here, if there is only X that is leaving out and a carbocation is getting generated here, if there is no oxygen that is present to stabilize this carbocation, trust me, is not that much stabilized, and the nucleophilic attack at this carbon is very slow. That is very slow. But if the oxygen is present in the neighbor, then what happened? It will stabilize this carbocation and will and will actually enhance the formation of that carbocation, right? Here also, if the carbocation is getting formed, this oxygen lone pair again stabilize this by forming how many membered ring? One, two, three, and four. Four membered ring. Again here it is getting stabilized by forming a five membered ring. By forming a five membered ring like this. So this is how it is going to form you the rings, right? So as you can see, which is the less strained ring, 5, 4, or 3? It is the high. Yeah, it is highly strained ring. 3 is the highly strained ring. 5 is the very least strained ring, right? So that is why the carbocation stabilization in the formation of 5 membered ring is very much, which enhance the nucleophilic attack very much, right? So that carbocation is formation is facile where it is more stabilized. So according to the neighboring group effect, the fourth one is getting stabilized higher, and thus the nucleophilic attack will occur at this very fast. But in the case of one, there is no stabilization due to oxygen. The neighboring group effect is not going to operate here. That is why the carbocation is not that much stabilized, and the nucleophilic attack on that carbocation is very much slow. Is it clear to all of you? Just give it a thought. Yes. Yeah. See, what I'm saying, there is a concept called neighboring group participation. What happened in that? If there is X which is getting leaved out according to the nucleophilic substitution reaction, right? So here the carbocation that is getting generated here is now stabilized by the oxygen lone pair. This oxygen will donate the lone pair on the carbon and will let you form three kind of rings according to the position of oxygen. You will get three membered ring, you will get four membered ring, and you will get a five membered ring. So I have told you the five membered ring is the most stable ring. 5 ring is very much stable ring. So that is why the stabilization on the carbocation at the fourth entry is very high. If the stabilization of carbocation is high, the probability of the nucleophilic attack is very, very high, right? So that is why the fourth will give you a nucleophilic attack very fast, then three, then second, and then one. So it will give you the nucleophilic attack very least. Is it understood now? Oh, yeah, option 2 will be the correct one, right? So this is it for today. I hope you got the answer. And if you have any query, please feel free to ask me in the next session, which is on Saturday, 6 to 8, right? So we will meet on the next Saturday, or I'm thinking to reschedule the class for the Saturday, I think. So I will get the permission and we'll reschedule it on Monday or Tuesday because I have to go somewhere on Saturday. So we will be rescheduling that on Saturday, on Monday or Tuesday, right? I will let you the time. I'll let you know the time, and you can join the class. Okay. So that is it for today. Thank you so much for joining. I hope all of you have gone through the questions and understand the answer as well. So I will be uploading this video to the my YouTube channel. If you don't understand anything is problematic, please go through that my channel, and again you can see this video. So these questions and answer will be available to you. So thank you so much. And now I'm just, yeah, YouTube. Yeah, yeah. Sure. I'm typing in on the chat box. Just okay. This is the channel name, so you can Google it on the YouTube, and you will find it. Okay. So these videos are available on that channel. Okay. So now I'm closing the session. Thank you so much for attending, and thank you so much.